Hello everyone and welcome to this talk. We'll be dealing with particularly two different problems that appear consistently intertwined in computer graphics. One of function reconstruction or regression, as you can see on the left, and the other being numerical integration or estimating the area under a curve, as you can see on the right in this picture. There have been several approaches to this in computer graphics literature with different types of bases. And they are used to sort of produce interpolants for functions given point evaluations. But these methods or these bases are also useful when we need to perform numerical integration. And of course, the natural question then is, why can I not just use a neural network as my interpolant? And of course, the answer is you can use it as an interpolant, but if you would like to know the integral of that function that the neural network represents, then it turns out it is not so trivial. There have been several methods that do this for specific neural networks, and I will leave the related work section out in this talk, but please refer to the paper for details. This brings us to the central sort of topic of this talk, which is a QNet, or a network that can be used for low-dimensional integration of neural proxies. Hi, I'm Kartik Subar from the University of Edinburgh. This talk is going to be fairly general. I would refer you to the paper as well as the accompanying video for a more detailed treatment of this subject. What I'll do is I'll start off with how can you actually use QNets and then take you through the various steps to give you a better idea of where it's useful. So how do I use a QNet? Typically, we're all quite comfortable with training a neural network given point samples of a function. On the left here, we can see a function over a two-dimensional domain evaluated at several points shown with triangles, and the value of the function at these points is shown using circles. And given these values, we can train a neural network that approximates the function and therefore can be used to evaluate this function at new points in the domain. However, what the topic of this talk is given that network, how do we estimate the area under the curve as shown on the bottom figure, where the blue area, the blue volume, represents our target. What I'll show in this paper is that we can take the weights of that neural network that has been trained, pipe that into what I'm going to call a QNet, and out comes the volume or the blue shaded region, which is the integral of the function over two dimensions. QNets are fixed weight networks that are parameterized by the dimensionality of integration. So for example, here we have a function over a 2D domain as shown above, trained first so that we produce learnable weights W. Then these weights are input to a 2D QNet to produce the double integral of f, while they're input to a 1D QNet to integrate one of the dimensions of f, as in this case, y. For details, please refer to the paper on how different subspaces may be integrated. Another advantage of QNets is that the subdomain or the domain of integration can be changed. For example, here we show two different integrals, both double integrals, but one over the domain D1 and the other over the domain D2. The procedure for calculating these two integrals is identical, but the weights in the QNet are adjusted appropriately in this case of D2. A third advantage of integration via QNets is that they accommodate input transformations, affine transformations to the input space seamlessly. For example, here, if instead of inputting x to the network to get f of x, if we inputted a transformed version, imagine a rotated image instead of an image, then the output would be f of t of x. And we show in the paper how integrals of transformed functions can be obtained without having to retrain the original network. Thus, in summary, all of these different operations can be performed without having to retrain the original network, which is one of the major advantages of using a QNet. The key insight behind QNets is easy to see. So for example, here we have a network with one hidden layer and one output layer. The hidden layer has an activation function that is a logistic function, and on the output layer we just have a linear activation. It has a one-dimensional input and 3 neurons. And we can see that in this case, we can write the output function f as simply the sum of 3 scaled sigmoids. Naturally, if we can write f as the sum of 3 sigmoids, then we can write its integral as the sum of the integral of 3 sigmoids. And it turns out in 1D, the integral is a soft plus, and this is fairly simple to do analytically. However, in high dimensions, we show that this can be written using polylogarithmic functions. We validated our estimator using QNets via different analytically chosen integrands first. Here we show the three classes that we used. First, we used smooth functions, which are just a mixture of Gaussians. Then we used a truncated mixture of Gaussians. You can see that the green region is the zeroed out space. And finally, we used hyperrectangles or collections of rectangles to represent a binary function, just to test the effectiveness on highly discontinuous integrands. We generated multi-dimensional versions of these up to dimension 12 and gathered statistics on how QNets performed when we tried to integrate them. Please refer to the paper for details. Here I show just a snapshot of what the marginals look like. So on the left you see a three-dimensional mixture of Gaussians. In the middle you see a set of plots which are 2D marginals obtained by integrating one of the dimensions, and you can see 3 of them a lot across the columns because each one results from marginalizing a different variable. On top you see our closed form solution, and at the bottom you see the reference. As can be seen here, the closed form solution matches the reference quite closely. On the right, we see 1D marginals resulting from a 2-dimensional integration of the function in 3D. Again, we see that QNets produce quite a high fidelity approximation for the marginals. Another example here that I'd like to highlight is that when used as a control variant, the QNets can be quite useful. For example, here we show 2 plots. On the left we show relative error, and on the right we show relative variance. On the x-axis we see nu, which is a parameter that expresses what fraction of samples were used in the Monte Carlo estimator. So to the very end on the right, we would expect to see 1 where all samples were used to integrate via Monte Carlo. At 0, we use 0 samples for Monte Carlo integration. Instead, we use all of the samples to construct the proxy, which is then integrated via a QNet. So if you look at this curve, the curve goes smoothly from just using QNets on the far left to using QMC or MC purely on the far right. Of course, we don't show the plot all the way to 1. But we show, using dashed lines, the errors and variances obtained using QNet, as well as MC and QMC. The red curve shows the behavior of QNets when used as control variates with different fractions for producing the proxy versus Monte Carlo estimation. Although the error doesn't reduce significantly, we can see that the variance does indeed, for a large set of fractional weights, go below Monte Carlo and QMC variance. One of the applications that I would like to highlight is that of inverse rendering. Here is an example of a bull placed inside a Cornell box scene with 2 parameters of interest. 1, the rotational angle of the bull about the vertical axis, and 2, the roughness of the material on the bull's surface. Our goal is to observe a small patch of pixels on the right wall, the green wall, and to predict theta 1 and theta 2. Of course, we can do this with standard inverse renderers that are available, such as Mitsuba 2, and we obtain point estimates across iterations. Just plotting these iterations, we see that for theta 2, depending on the size of the patch observed, we get different estimates. So the first plot on the right shows these evolving across iterations compared to the reference value, which is shown as a horizontal dashed red line. What we also did was gathered all these point estimates and produced a histogram, or several histograms, one for each window size. And we can see that for some window sizes, the mode of the histogram points to the true reference value. Of course, this is all with point estimates, and what we wanted to do was to take a Bayesian approach to this, where we would get a distribution over each of these parameters that would point to what the reference values were. Using our method, we can see the plots on the right for both theta1 and theta2 evolving from light gray to dark, almost black. And we can see that over several iterations, the distributions evolved to predict what the ground truth values are, which are shown as vertical dashed red lines. What we can see from this is that in addition to just predicting what theta1 and theta2 should be, they do indicate what the confidence is. For example, here, the method was much more confident in evaluating the rotation angle than estimating roughness. Another application that I'd like to show you is that of procedural noise. If the original network or the proxy was not trained and was initialized with random noise, then we get textures as seen on the top left, for example. However, the noise can be then manipulated to produce anisotropy, as shown in the top row of noise textures. But what the QNet allows us to do is to provide integrals over different bounding rectangles, which then can be used to produce samples as shown in the bottom row. So in the far left in the bottom row, we see a noise texture, and we see three different sets of samples. And as the sampling density is increased, we see that this tends to the noise texture. Again, because we can evaluate integrals via the QNet, we can actually perform these samples without evaluating the noise function even once. A more classical application, such as estimating optical depth along rays. On the left, you see a smoke simulation in Blender. We took a central slice, visualized it as a heat map, and showed three different camera views, generated rays along each of these camera views, and estimated the optical depth along these rays using QNet and compared them to the ground truth. Yes, we know that neural networks are powerful tools to approximate functions. We know how to use them to reconstruct functions, but very little is known about how we might integrate the functions that these networks describe.